Thus far, we've been able to provide an overview of various strategies that we can utilize in order to ensure efficient page replacement. And so this is consisted of understanding various page replacement algorithms that we can use, such as Vellity's min, first in, first out, true LRU, approximate LRU, approximate LRU number 2, as well as second chance replacement. And these various algorithms rely on different hardware components in order to assist. And so now let's return back to understanding the impact of these memory management strategies on our processor pipeline design. And so with our 5-stage pipeline processor, we have to take into consideration appropriate components that will affect the performance of our virtual memory. And so you want to consider with virtual memory, for every memory access, it's going to require 2 memory accesses. So this consists of getting the page table entry as well as the actual memory word from memory. And so what are some of the downsides that this approach will take with our pipeline processor design? And so those problems result in inefficiencies in our pipeline. And so essentially what that means is that for at least every instruction, we're going to need to incorporate at least 1 bubble into the pipeline. So we need to figure out a way in order to get around this performance degradation. And so one thing that we can consider is that we want to make sure that we're able to efficiently look up our physical frame number from our page table. And so the physical frame number is what we'll use to correspond to our virtual page number and our virtual address. And so this requires that we are able to translate the page table from virtual to a physical address. And with this page table residing in memory, we're essentially going to need to utilize 1 page per process. And with this in mind, the CPU is going to need to know the location of that specific page table in memory in order to carry out appropriate address translation. Now, the problem that we have here is that with our physical frame number, the entire page table won't be able to fit in registers. But we're able to include a subset of the page table that can fit into registers. So with this in mind, what if we could add a small table into the process in order to help minimize performance between a context switch? So why would this approach work? If we have our physical frame number and accessing, it will work essentially based off of the idea of locality. And with locality, what we want to consider or keep in mind is that sequential instructions are likely going to be using data that is related to one another. So if you have instructions from instruction 1 through instruction 5, it's very highly likely that those instructions are going to use subsets of data that need to be shared between instructions. And so you'll have contiguous data that can be utilized. And so the set of pages that we are going to use to represent this locality is what we will call a working set. And so we want to consider our translation look-aside buffer structure. And so the translation look-aside buffer is going to be a table. It's going to contain various fields that are similar to what we have here. We're going to have a field that denotes whether it's a for the user space or kernel space. We have the virtual page number, the physical frame number, as well as if the data is valid or invalid. And so the goal of this is for us to be able to minimize page faults, because page faults can be disruptive to system performance. And so with this in mind, our memory manager is going to focus on trying to minimize page faults. And so it's important to keep in mind that when we have a context switch, then there are going to be several instructions that could result in a timeout for the system. So what we want to do is be able to speed up address translation. So with this in mind, we're going to need to try to split up our physical components. So initially we have our CPU that is going to connect to our virtual page number, and we have our physical frame number that is going to need to be retrieved from our page table. And so we can't get the entire page to fit, but we can get our subset in. And this is where we will utilize our translation look-aside buffer. And so with our TLB, we're able to pull the appropriate data that we need from our physical frame number using our translation look-aside buffer. And so if we have a TLB hit, then that means that we have the necessary data that we need, and we don't need to insert any bubbles to retrieve that data from memory. Conversely, if we were to have a TLB miss, then that means that we'll have a slow path, and that we'll have some bubbles that need to be inserted while we retrieve the data from memory. And so if we go back to our TLB structure, you'll want to consider that we have our user space and our kernel space. And each one of these entries is going to be specific to each process for our user space. But with our kernel space, each entry is going to be the same for all processes. And so with this in mind, the benefit of how a TLB works is that it's a general case of memory management called caching. And caching is when we are going to store data that we're likely to need in a small register for quick access. And so with this in mind, we can say that the small table that we have for our TLB is a type of caching that we use. So what might be the implication of the U entries if we have a context switch? And so if a context switch occurs, that means that we would have to flush out all of our user entries in our TLB. And so in order for us to make this work appropriately, and once we flush out those user entries, the valid bit is replaced with invalid for all of the user entries. So in order for this to work appropriately, we're going to need to incorporate some new instructions. These instructions are going to be there for purging of the TLB or a TLB flush. And we're going to need to determine who can execute this instruction. And so our choices would be in the user space or the kernel space. And for this to work, we're going to need to have only the kernel being able to execute this instruction. So this leads to our question. Upon a context switch, we have a few choices. What could occur? We can have A, the entire TLB is flushed. B, only the kernel portion of the TLB is flushed. C, only the user portion of the TLB is flushed. Or D, no change to the TLB. And our correct answer here is going to be that only the user portion of the TLB is what is needed to be flushed from our space, given a context switch. So you want to consider the nature of a process, and that there's going to be a trade-off in work in terms of bursts between CPU activity as well as IO activity. And so with this in mind, we want to be sure to increase multi-programming so that we're able to keep the CPU busy in order to complete appropriate useful work. And so when we think about CPU utilization, what we want to think or what we see is we have the CPU utilization. And if we're able to increase our degree of multi-programming, then this is going to result in higher utilization. However, that is not always the case. And so if we do a detailed analysis of our utilization curve, we can identify that there can be a point that occurs in which performance tends to degrade. And so this typically will happen in a system when we have too many processes that are asking for memory. And so what might be the downside for too many processes that are asking for memory? Well, essentially, it is going to result in an overcommitment of memory or resources. And so with this in mind, we'll have a bigger working set than physical memory is able to hold. And so with this in mind, it means that so many processes are asking for memory that no work is being done appropriately. And this results in a concept that we call thrashing. And so thrashing essentially is a simple concept that we say when the system is not getting any useful work done. So what we want to consider is what paging is, that is implicit of input and output on behalf of a process, and the system can become IO bound. And when this occurs, the throughput is going to drop precipitously. And so in order for us to minimize thrashing, what we want to do is create what we can call a working set. And essentially, what is a working set? A working set is going to be the set of pages needed to keep a process from paging. And so with this in mind, we can have a number of different processes that are executing, and we have a specific time period in which they execute. So what we see here is for our working set, we have our process and the virtual page number. And then each process is going to execute at a specific time interval. And so what we're able to see here is that from the time slice of T1 to T2, we have P1 and P2 actively working. From the time slice of T2 to T3, we're able to see that we have P2 and P3 actively working. From our time slice of T3 to T4, we're able to see that P1 and P2 are working again. And then from T4 to T5, we're able to see that P4 and P3 are working. And then from our time slice of T5 to T6, we're able to see that P2, P3, and P4 are working in memory. And from our time slice of T6 to T7, we have P2 and P3 working. And then from T7 to T8, we have P1 and P4 that are working. And so essentially what you want to consider is that the working set is going to denote the number of page frames needed to the working set size is going to be the number of page frames needed to hold a working set. And so the working set is what we use to define the set of pages that will represent the activity of a program. And of course, as we shown here, the working set can change over time as well. And so we have distinct pages that are being utilized. And so for our working set from T3 to T4, as we mentioned, we have P1 and P2 involved. And conversely, for our working set of T7 to T8, we have the P4 and P1 that are actively working during that interval. And so another construct that we have to keep in mind is called the memory pressure. And the memory pressure is going to be the summation of the working set of all the processes that are currently competing for appropriate resources. So we can represent this by a summation of all of the working sets that we use from P1 to so forth, and those are all going to represent processes in memory, each with the working set WSSI. And so we'll consider that the count of active processes will signify the degree of multi-programming needed. So what we want to consider is how do we control the degree of multi-programming? We want the sum of our working set to be greater than the total physical memory. If that occurs, then we'll have to swap out some processes. And then if the sum of our working set is less than total physical memory, then that's when we want to increase the degree of multi-programming that we have going on. And so utilizing working sets and understanding memory pressure is a tool that we can utilize to determine if we're effectively making use of our CPU and memory resources. And so you want to consider that, if we are having total memory pressure that is going to be exerted on a system, if it is greater than our available physical memory, then we need to figure out a way to improve our memory management and decrease the degree of multi-programming. So with this in mind, if the total memory pressure is going to be less than the total available physical memory, then we're going to need to improve the memory pressure. And so what we want to consider that is, as page faults increase, we want to find a sweet spot that occurs between the number of page faults that might be too much versus the number that are too low. And so what we do is we call this a sweet spot. And so the sweet spot is going to represent the increase, the point in which there is a evenness between the number of page faults, too many page faults versus too little page faults. And so if we have too many page faults, we're going to need to lower our memory pressure. And if we don't have enough page faults, we need to raise our memory pressure so that we can find the perfect balance between those. And so one thing that we have to keep in mind is that page faults can be very disruptive. And so specifically from a process point of view, we have our implicit IO that causes page faults to be disruptive. And from our CPU utilization perspective, the overhead doesn't necessarily contribute to the work that we need. And so in order for this to be accomplished, we'll need to limit the impact of our page faults so that we can improve the system performance. And so one way that this is done is that we want to keep a small pool of free frames. And so with this in mind, we overlap the IO with processing. And then we want to make sure that we don't wait to start our page replacement algorithm on a page fault. And so when it comes to page replacement, we want to ensure that background activity of the OS is limited when the CPU is not in use. And so if we have our free list of components, what we want to do is look for a clean page frame. So since our first page frame in our list is dirty, we move on to the next. And so this becomes one that is clean, and that then will become our victim. And so another concept that we can utilize is reverse mapping for a page table. With this in mind, it gives us a third chance for reuse of a page before being kicked out. So if we want to consider that we have P4 is running and it page faults on VPN 33. So we don't need to go to disk. What we want to just do is remap the PFN 52 into our page table for P4 for VPN 33 and take it out of the free list. And so with this in mind, another concept that occurs with virtual memory is going to be segmentation. And so when this occurs, we'll have a segmented virtual memory. And so segmentation allows for a process's memory space to be subdivided into chunks of memory that can be associated with specific aspects of the overall program. So we can have segmented virtual memory to help manage complicated system architecture. Segmented virtual memory was first introduced in the 1960s, and it's visible to the ISA, so it doesn't work as a retrofit to ISA with contiguous memory models. And so that means that it needs to be implemented with regards to the ISA. And so we can have various segments that can be utilized. And so we can have code segments, we can have global data segments, we can have our heap segments, as well as our stack segments. And so these are all representative of different ways in which we can utilize virtual memory. And so what does a segmented virtual memory look like? It's going to have the process address space divided up into n distinct segments. And so for each segment, we're going to have a number as well as a size to represent the segment. Each segment will start at its own address of 0, and it's going to go up to its size -1. And the typical format for the segment addressing will be that we'll have our segment number as well as our segment offset. And so we can have an example of a segmented virtual memory. In this, we have an application that is going to process input from a camera. We have the camera input processing that occurs. Then we have a video analysis that occurs. Camera prioritization occurs, and then we have an inference engine that is utilized. And then we're able to utilize our database for archiving appropriate information, and then also determining if appropriate alerts need to be generated. And those alerts can then be used to trigger alarms or warnings on various devices. So in this case, we can have an appropriate segment that is going to represent camera processing, appropriate segment that will represent our video analysis. Segment 2 is going to be representative of our camera prioritization. Segment 3 is going to be representative of our inference engine. And segment 4 is going to be representative of database archiving, as well as segment 5 is going to be representative of our alert generation. And so each one of these segments can then be mapped into our physical memory as well. And so we can have our correlation for our segment for the camera processing. It has a size of 4K. We can have our segment for the video analysis, which has a size of 20K. Our camera prioritization segment has a size of 12K. Our inference engine segment has a size of 18K. Our database archiving segment has a size of 10K. And then our alert generation segment also has a size of 3K here. And so if we want to represent the hardware needed for supporting segmented memory, it's pretty straightforward. We'll have our segment table that is going to be represented as a data structure similar to our page table. And then we'll have our segment descriptor, and that is going to be a part of each entry in the table. And with the descriptor, it's going to be able to essentially give us the start address for the segment, as well as the size of the segment as well. And so for each process, it's going to have its own segment table that's going to be allocated by the operating system. So in this regard, it's similar to paging, but it does require a special register called a segment table base register in order to implement it in hardware. So for each segment, we have that start address as well as the size. And then we'll have appropriate bounds check to determine if we need to access memory as well. So one thing to keep in mind is that this could be an opportunity for external fragmentation. So one thing that we want to keep in mind with page segmentation is that page tables can be big, and we're going to need one for each process in memory. For example, we could have a 64-bit virtual address with 4 kilobyte pages. And so that means that our VPN is going to need to be 64 minus 12 or 52 bits long. If a page table entry is 64 bits, then we need to determine how much space is going to be needed. So we can have 2 to the 52 entries times 2 to the 3 bytes, which is going to work out to 2 to the 55 bytes, or 2 to the 15 times 2 to the 40 bytes that are needed. So that's going to be 32,768 terabytes. And we need one for each process. So as you can see, that presents a big problem that can occur with our page segmentation. And so for our address space, for our page segmentation, you want to keep in mind that we'll have our segment number, the page number, and offset. We're going to have the descriptor base register that's going to map to our segment descriptor table. And then we can have a descriptor for our segment that maps to our page table for the process, as well as our virtual page. So this provides us with an overview of understanding how we can optimally use virtual memory in our systems for our pipeline processor design.